Okay, hello everyone. Can anyone hear me? Great. My name is Matthew Tovbin. First of all, I'd like to thank everyone for joining this conference, come to my talk. Please use the app to rate the talk. If you rate 5-star, you'll get a free data set to play with. Absolutely random, unique data set of data. Can guarantee you uniqueness, that's for sure. So my talk is named How Truth to Be a Liar. It's actually, the name has nothing to do with the talk itself. But so the subtalk, it's basically I'm going to talk about the type safety for machine learning and how we solve it with Spark and Scala at Salesforce. So any talk should have something beautiful in it. So I started with this nice little quote. When I originally read Shakespeare, I actually read it in Russian. So it was quite beautiful. And then I read it in English, which was even better. So let's just look what I'm going to talk about. I'm going to give you a very short intro into machine learning, like real machine learning 101. Then I'm going to be talking about the real-life machine learning problems which we have been solving and solving currently at Salesforce. I will show you a tool application for Titanic data in Spark ML. Then I'm going to show you how we can add types on top of it with Scala, and then some coolness behind the scenes how this whole thing works. So what is machine learning, right? It was defined well in the IBM journal in the 1950s, the capacity of a computer to learn from its own experience. So it can modify the processing of the function based on the newly acquired information without modifying the code. So this is actually a very important property to allow us to code to scale. So what is an experience? Experience is just data. So we feed data. We hope the algorithm will get better in its own execution. And this is, in essence, what machine learning is about, to build enough sophisticated software that it can learn from data using mathematical models or something else, or a combination. So machine learning solves a variety of problems. We all know some of them at least. Some kind of prediction, for example, where you want to predict what's the, in any consumer product that we use, some kind of prediction that what would you like to buy or what would you not. In diagnosis for cancer treatment and other things, medical diagnosis, it's all over the place. Forecasting, planning. I'm actually going to be more focusing on the forecasting and prediction rather than everything else because this is the most interesting use cases for us. So when you build a machine learning model, right, where a model is your algorithm essentially that you would use to build those prediction and forecasts, you always start with some data set. So your data set can be in Excel format, can be a log or semi-structured log or some other chaotic information, maybe some signals, maybe images, anything you can think of depending on the domain you guys working on. And then you would start by doing some feature engineering. This is what you would do by the book, literally. Okay, you want to pick certain signals from your data which make sense to you because you're the owner of the domain. You might say, okay, this column is important, this is not, etc. Then you run the process of model training, where after you wrote some of the code that knows to recognize the correct features, which mathematical model you want to write on top of it. Is it either logistic regression, random forest, etc. Anything you can think of would then run on top of your data. Once you trained a few different models, which you usually do while you're experimenting, you need to define some kind of evaluation logic, which either takes some kind of golden sample data or uses the same data by using train validation split and uses this data to verify that your algorithm actually performs correctly on the data, and it doesn't produce some nonsense predictions, and the predictions are at least as good as you expect them to be. So this is what you would find in most of the books on machine learning. This is like the pipeline that you would go through and any machine learning engineer would do. In real life, it's a little bit different. It's rather than building a model, you would actually build a whole different pipeline. You would actually usually have multiple data sets which produce data in different various formats. They not necessarily overlap, and we are humans should actually make sense to those data most of the time. I'm not talking about the deep learning right now, but most of the time we actually know what data is important. And this data, say, it flows in different cadences. Let's say an example of actual systems. You have maybe a user profile, like a user Facebook profile, and then we also want to track all the user clicks on different merchandise websites, like all the purchases that this user did. So we want to get all this data, join it with the user profile, and then make maybe some sophisticated prediction on that user. To do that, we need some kind of ETL process now. So we need to aggregate the data from those data sources, build some intermediate format from it, and then do the feature engineering, again, model training, train multiple models, perform model evaluation. But once we did that, it doesn't end here. It actually moves further. Once we evaluated model, we actually might want to redo our features. We found out certain features that don't make sense for the certain model, for certain prediction. Or we want to retrain the same model. And this cycle can go on and on until we kind of finally satisfied. Ideally, we should also automate it, right? We don't want to have a manual process there. We don't have person, which actually happens a lot in businesses when they have dedicated data science team, which all their jobs are just look on the data, look for some interesting patterns, and provide predictions for the businesses. Once you evaluate and you're satisfied with the model, we actually go to the deployment phase. Deployment is something same as any web application or any other service that you would work on. You would deploy it on some service, so it will serve the scores back to the user, serve the predictions, the forecasts. Actually, there's an interesting fact. So in order to provide a scoring, so for given user, what's the next best purchase, like give a prediction for the recommended products, for example, I would actually need to perform the same feature engineering for the user profile, so it will make sense for the model domain. So I hope I make sense here. So in order to compute my function, I need to make sure the input values have the same number of features, they have the same domain. Otherwise, my predictions won't make sense. So after I did the scoring, I can finally serve the happy users. And another interesting piece is that scores are actually being now pushed as an extra feature into my data domain. So my scores can now serve to be used to build other predictions. So this is something that is also quite unique when you start doing the real-life machine learning. So if I predicted certain list of products, now maybe I want to train another model for the likelihood purchases for that user, to maybe for some marketing campaign. So this is more or less how it looks in the real life. So I'm going to mention some problems with it, right? So ETL is a difficult problem. I'm not going to mention it, so you read about it. Feature engineering, basically picking which features are good, making the permutation of the features, making them fit your model is actually even tougher, because the number of different features that you can produce from the data is exponential. So you don't want to waste your time on trying all the possibilities. You actually want to do some smart selection of features. Other things to mention, for example, okay, your data science team built some prototype in R, Python, Octave. It works great, but they actually can't deploy it to production. It doesn't scale for the data sets that we really want to apply on. Even the logs, like sometimes it seems, okay, it's very easy. We're just going to regex on this and then extract certain timestamps and then do some predictions. It's when you multiply number of logs by number of machines, actually it explodes really fast. Also number of features. Copy pasting code obviously doesn't work for the small projects, of course. Never works. And then this is my favorite part. So model training fails exactly 2 hours after you go to sleep. Not 2 hours, maybe like 4 hours, but it happens all the time. So you spin up your model on Spark or whatever software you use, maybe like TensorFlow, you run your training, a few hours later it fails due to some division by zero, inconsistent outline label, serialization issues. Data is not there, you fail to find something. So data is there, it's insufficient, so basically you don't have enough positive samples, for example, or out of memory, insufficient space. Serialization is something like, it happens all the time, right? It's like you use Spark. Spark and serialization, I think these are the two synonyms for me. So now we have all the models and scores, right? How can we trust them? How can we provide a significant kind of insight for the users to say, okay, you can trust the score based on ABC, because like, how would we prove correctness? This is a very tough question. I'm probably not going to touch it much in this talk. It's like something for you to think about. So specifically for Salesforce, a couple slides on Salesforce specific things. So we have a multi-tenancy problem. Well, it's not a problem, right? It's like that's what our business is. We have multiple customers, so we build a CRM for all those customers. They have different variety of data stored in Salesforce, and now we want to build a machine learning platform for them. So we have an extra 5 dimensions here. Multiple customers, multiple environments for those customers. We have different data sources because each customer can be using different Salesforce cloud, so they have different type of data, different cadences. And then they have different data entities. And now they want to build different applications. For example, lead scoring, right? How the salesperson can sort their leads when it's business day starts. So which person should he email or call? Which person should he reach out first or not? Same with predictive journeys, maybe like marketing campaigns for emails or so on. And then we have, of course, all the things down here. Security, scale, automation, as I mentioned before, transparency for the user, and the cost efficiency. We want to make sure our machine learning trained and score in an efficient manner. So that's why we actually went and built Salesforce Einstein. This is our offering for machine learning. And it's a machine learning platform for customers, engineers, and data scientists. We're trying to target it for all the audiences, so the person won't need to do ETL or have a PhD in maths or stats or anything like that. He can just mostly drag and drop features or drop a few lines of code and have his predictions ready. So we have acquired Prediction.io. This is one of the startups that's joined my team. I don't know if you guys are familiar with it. I hope you are. If you're not, check it out. We're trying to make it a top-level Apache project now. And then we developed Optimus Prime library. That's what I'm going to talk next. This is in-house transformation framework for Spark and Spark ML, where we provide type safety, mainly for the transformers and estimators. So how many of you guys do Spark here? Okay, most, like half, right? So we will see a lot of things that you're familiar with. Whoever is not, it's going to be a good introduction on bad and goods of Spark. And of course, we build a lot of services, like microservices and run it on Amazon with DCOS, and we do it in Scala. So right now, I'm going to walk you through a process of building a machine learning application with Spark ML. Like, if you would start Spark ML machine learning application, that's what would you have to do, more or less. So let's say we have a data set of all the survivors on Titanic, all the passengers of Titanic. And then we have this Boolean, whatever, like numeric value that is a person survived or not, 0 or 1. I want to make a prediction based on which properties of those of what we know about passengers contributed the most to their survival, or not, in addition to a chance, of course. So in Spark, you would start with a bunch of imports, and you would start from spin up Spark context. So Spark context is something that you would host your Spark application. After that, you would start defining some kind of read function for your data. So I picked up here a data frame format, because this is something that we actually use the most. Some people already started, like since 1.6 you have the data sets, which kind of bound to case classes. So not all our information fits in a case class. That's why we actually use data frames. But this is typically what you would do. You would define some schema. So you would name your columns and types in some format, right? Either in a case class or in a struct type here. Then you would say, okay, SQL context, read the format, say in the CSV file with the schema. And after that, say I want to do some renames. So my fields will be, say, all lowercase. So I'll have to do this. I'll like survived, so lowercase survived, sex is lowercase sex, age, and so on. Eventually, the read data produces me a function to read the data frame from a file. So val row data will contain the contents of the data. At this point, I actually might get a runtime exceptions. Like if the file is not there, or maybe the types are incorrect, the types that I defined. Well, actually, types can be anything if it's castable. So if it's not castable, you will get a runtime exception. But sometimes you just don't get an exception, especially if it's a string type. And it's nullable, for example. You kind of got lucky enough, so all your values are nulls. And so it's something that we would like to fix. So now let's say I wanted some features to my data set. I want to compute, let's say this is like a part of feature engineering. Let's say I want to compute a family size for the passenger. Well, in Spark, you would define a UDF. It's like a user-defined function that would get some inputs and will compute an output. So in this case, it takes two fields, siblings, poses, and parch, which is like parent-children field. Does the sum and +1, which is myself, and then produces the value. And now, I really don't like the way they did it in Spark, but somebody can argue, but you actually need to take a data frame and do data frame with column, set a new column name, and then apply a function. So it's like literally full freedom here to overwrite existing columns. Now, like imagine you have a lot of modules like this that kind of other teams wrote, and your team also did, and then maybe you forgot the column name. You can literally override the data. It will be very hard at the end to track it back from the predictions, why my scores are suddenly lower by a few percent. So it's something that we would like to fix as well. So now let's say I want to fill some missing values, because machine learning problems and anything else, right? We don't like nulls. We want to inject some concrete values. So let's say I want to compute an average age and replace it with for the missing values. If I don't have a passenger age specified, I'm going to need to inject an age. So here I actually performing a concrete computation on data frame. I'm doing data frame.select age, and then I'm doing aggregate average age. .collect actually does the reduce. It actually goes and does the reduce and the shuffles and everything. It's a compute-intensive operation, which is now hidden in this little function. Again, if you want to share this code across the teams, it's very difficult to track it afterwards. And then you get only you get the value, and then you produce, you inject it instead of the missing one. Like you do a df and a.fill. Same with embarked. I want to maybe replace if the station of embarkment is not provided, I want to replace it with a default, like a Southampton with a letter S. So I'll have to write a UDF and so on. So once I have those two functions, now I'm actually modifying my data frame. I would do fill missing, add features on the raw data. And now you see this little cache there. So if I'm a data scientist, I have no idea what the hell it means even. I need to have a team of machine learning engineers and a data scientist to collaborate with each other, which one team would say, okay, you need to cache your data if you're going to extensively use this data set down the lines. And I need to remember about those things every time I actually build in my logic, which is also kind of removes you off the boundary of your problem into the data problem. So in other words, what I'm trying to say is that your business logic and data manipulations overlap. So now I want to split the data, right, into the train and test set and cache it as well. I need to remember to cache it. So I would say 75% of my data for training a model and 25% of my data to test it. So once I have that, I will start building a pipeline. That's how you do it in Spark. You would apply some string indexers for your data. Then you would concatenate all the fields together and then finally build a vector from it. Vector is a numerical array, basically, of data, which then logistic regression can feed from. So that's where I do. Like in this case, I really did a toy example. Okay, logistic regression set input column, it's like feature vector, and then set label column survived. And then finally, I build a pipeline of all those stages. So I'll have like string indexes first, like it's from left to right, like DAG. String indexes first, then the vector assembler, then the logistic regression. Essentially, what I get from it, well, it's not yet. Now I want to specify the grid for the parameters. So in machine learning, you do something like a hyperparameter tuning. You want to make sure you fit your model with the best set of parameters. This is what the param grid builder is for. And then you want to do cross-validation with some evaluation. This is the evaluation part, where it would allow you to pick me the best model. And that's where I do it. So I actually do cross-validation to fit on the trained set. I get back a model, cross-validation model, which will contain eventually the logistic regression instance with some set of params that it took from my grid. And then I can use this model to score. So this is like more or less in 5 slides what would you do in Spark to train a model. So the good parts, right? Like kind of simple abstraction of the logic that you would do. More or less, you would do like transformations, which are maps, and estimators. So you remember we computed the average age. This is like the estimator. And then the pipeline where we stitch it all together. It's like one last line that says, okay, this is the order of stages I want to supply from a machine learning pipeline. So we like that a lot. Serialization allows us to reuse the models, right? I didn't mention that on the previous slide. We have this model.save. So I save the model, and I can reuse it for the later use. Right? You can load it to do the deployment on some separate service now. They have fairly good implementations of various estimators, like word-to-vec, logistic regression, random forest, Bayesian, and so on. You name it. They have a lot of good stuff already implemented. It's kind of all-in-one platform. So Spark and Scala, they have actually, it's a good symbiosis for just ad hoc prototyping with machine learning, with a fairly large data set especially. I mean, usually people start with something in Python and kind of move on fast enough to Scala, where we have a large enough data set. They do have support for Python as well, and of course Java, like nobody uses it, I guess. But Python, yeah, so it's pretty okay. It's okay. So Spark ecosystem is healthy, which I like. It's not the same nice graph for the other projects out there. So actually kind of keep up with the issues really well. Okay, the not so good parts, right? So the things I mentioned, no type checking. So transformers and estimators can override everything. Like there's literally no compile time check or anything. My pipeline can fail in a few hours. Interfaces are way too open, so you get a data set, you produce a data frame. So data frames are kind of ugly, and they're everywhere. So once you start kind of playing with Spark, even if you start with the data sets, they're actually still very limited in their functionality. And you can kind of either fall back to RDDs, but they're slow. So kind of in the middle ground is data frame. So literally like untyped data set of row. There is really poor integration with ML vector. So this is actually a kind of niche problem, but you would discover it if you start. There's literally a lack of support for common I operations. If I want to do join and aggregate, or maybe like different, say I want to do conditional window join, or window at aggregation, that would be difficult. Schema and algorithms, I mentioned that definitions are interleaved with data manipulations. Okay, so can we do better? Yes, we definitely can, and that's what I'm going to show you. How do we do it with Optimus Prime? So Optimus Prime is essentially a transformation framework or a library to develop typed ML pipelines with Spark. We're trying to kind of in Zest to build some declarative and intuitive, very simple syntax that if you know how to program with any regular, any high-level language, you will be able to build your machine learning application the same way. So at least as easy as it is, as it gets. We want to have some typed operations, so we'll get the errors earlier. And then we want to have some reusability in the library for the I/O operations, features, transformations, so we can stitch different stages together in a very intuitive way. We definitely want to separate application logic from the data frame manipulations. So that's like probably was the start point of it. Like we didn't want people to remember about the data frames, which they shouldn't, right? I just want to take a couple columns, do some kind of manipulation on those, and then run an algorithm. Like, I don't need to remember about caching or anything like this. And then, of course, we want to build multi-tenant applications. We want to build applications that can work on a variety of data sets, that not necessarily work for one particular data set. Maybe we want to build a data set that groups values by types and applies certain set of transformations on those out of the box. So let me show you some code on what we've built so far. So I will do the same example now with Optimus Prime. And it's already, you can see it takes 3 slides. But I actually cheated a little bit because I put out the schema into Avro format. So it's probably going to be 1 extra slide there. So you would start from import. And as you notice, there is no Spark import. And the reason for that is that we actually not that depend on Spark. We currently build it for Spark, but it can be executed on other execution engines. So you would start from defining a reader. So reader incorporates some definition of how would you read the data. So in this case, I'm defining some simple CSV reader that reads the types of, it commits to return a passenger type. So you get a typed reader, and that's where your type starts from. So I lock it into the passenger type in this case. Once I have that, I can start defining some features. So for this, we have like a feature builder. Feature builder.binary says, okay, I want to define a binary feature of the type passenger, and I will provide you the extract method. So the extract method will take passenger, run the method getSurvived, wrap it into option, and then maybe I want to map the value if it's 0 or 1. And I'm going to say, okay, it's a response feature. As a result, I'm getting some containers, type-safe container that now knows that it came from passenger, and the result is the binary feature. And that's how I do for the rest of the features. As you see, I don't even name them because names are inferred from val names. I would explain it a little bit further how we do it. But this is the beauty of it. So basically, we're trying to leverage the uniqueness of variable names and scope and make sure you don't step on your own toes by overwriting columns and data frames. But don't think about data frames, right? They're not in the picture yet. So I just defined a bunch of vals here with some extract methods. So, okay, but they're all typed now. So gonna follow the thing here. It's okay, the passenger everywhere, it's all typed, and then all the vals here are of type some feature of some passenger to Boolean, or passenger to numeric, and so on. Okay, so now let's do some feature engineering. So instead of that family size now, I want to just do plus operator. I want to do siblings plus parse plus 1. Essentially what it gets me the feature like. Some other container that is numeric. Right? No UDF, no data frames again. Same with the age field. So I would like to do age.field missing with min. I want to have some right-hand operand to apply on my feature and get an extra feature back. So feature is effectively a monad. Same with the rest of it. Like embarked field, I do embarked field within with, and I provide some value to replace it. And that's how I would create a feature vector. So no ugly vector indexer, nothing like this. I would build a sequence of features, like as a large set of what types I want to include in my model, and I would run some vectorize on this. As a result, I get feature like again of vector. Okay, now model training. So model training, some kind of ugly thing happened here with a slide. Okay, so I would create a model selector where I would provide a set of algorithms. Yeah, I don't know what happened here. Yeah, it's all messed up. Okay. Damn. So model training, it actually shows correct on my screen, but it's not on yours. So I would create a model selector that would pick a list of algorithms here, not only logistic regression, but you can specify multiple algorithms. And then eventually you would do the Spark. Yeah, this is unpleasant, sorry about that. Anyway, you probably will download slides online if you wish after. So I would summarize that everything is typed. All our readers, features, pipelines, and models are all typed. They're tied to the passenger and the feature types. The syntax is kind of simpler. You don't have to remember to stitch stages together. You just do your mathematical operations, like with the plus signs and right-hand operands. Features are always unique in the code block, thanks to the val names, which we infer using, you will see now how do we do that. And then there is literally no data frames in the picture. People don't see data frames. Damn, I want to show you those slides. Oh, no, maybe like this. I will just drag this here in this, and then you will be able to see this last slide. Almost there. Yeah. I'm not going to do that. That was a very dangerous operation for the mirroring. So can you see this one at least a little better? Okay, I can see it from here. Okay, good. So I would create a model selector now, right, where I specify all the params for all the algorithms all together, because that's what I want. I don't want to train only the logistic regression. I actually want to train multiple algorithms at once. And I would stitch it into the pipeline, yes. But in the pipeline, I actually want to specify only the latest stage. Like I don't care what's the order. I'm just saying to the framework, okay, you go figure it out. This is my model selector, which depends on those stages, which those depend on those stages. Go figure it out, and then compute me the pipeline. And only now I spin up Spark. So Spark is actually like a punchline here. Okay, we spin up Spark, and we really need Spark to run the train method here. Like this little train here, this is where we need the Spark, because this is our execution engine. We need to run this computation somewhere. And the rest is the same. You get the scores, you save your model. Okay, I'm going to go back to my original mode and hope nothing breaks from this point. Awesome! And now it works. Thanks, PowerPoint. So, okay. We all already enjoyed the slide, so I'll move on. And now let's see some behind-the-scenes coolness, like how we build it. So we kind of went there and said, okay, what is missing from SparkML? SparkML didn't have proper rich type definitions. If you start messing with SparkML, you would see they have a set of primitive types, which are double, long, and so on, string, boolean. And then they have a little bit more sophisticated, such as arrays and maps. User-defined types are deprecated. I don't know why they did it, but I mean, they have to fix this at some point. But then what if you want to have sets? What if you want to have map of sets or map of sets? Something like this. Something a little bit more complex. Or if you want to talk more real-life scenarios, maybe you want to do, say, an address field where in address it's a composite object that contains a zip code and an apartment number and so on and so on. So we defined our own type hierarchy. Then we went there and said, okay, the transformers needs to be typed, and of course there are multiple types of those. And transformers, what they do, they take a feature in, they transform it, and they produce back features. So this is our monadic map operation for the features. So estimators are essentially reduces, right? They take a column of data, they compute a single value, and they become a transformer essentially, right? Actually every single machine learning model is actually, right? My model is an estimator. It takes multiple columns as an input, produces essentially a set of binaries, which then become a multipliers during your scoring process. This is very simple. It's all MapReduce here. And then pipelines, they kind of stitch it all together. So they would say, okay, I will need a data reader, which is, we kind of moved it away, right? This is the guy who provides the data for us, or kind of data definition. And then it will use the reader to read the data. And features actually also, they become an input for pipelines. So as we saw, like pipeline.setInput, we give them a feature. So features are materialized based on the reader. And essentially, pipelines become transformers to produce scores. So I think this is globally the picture you want to keep in mind after this presentation. So, I was trying, I spent like a few hours to present it nicely here. And then data readers, of course, they can be joined, so they also monad, and they have a join or aggregate operation on them, which doesn't do anything. It just kind of builds the reading graph to be used by the pipeline for the run. So something like actual code. Okay, feature types. So this is actually some internal pieces from our code. So we went there and defined, okay, let's just start from simple things. So we defined some simple aliases for types, for Scala types. But this wasn't enough. We kind of actually wanted some rich types, such as email, phone, like URL, as things that I mentioned, like an address. So we ended up with this. This is, again, not a complete picture, but it's like a type hierarchy that we defined for our types. We leverage a lot of things from Algebra, Twitter Algebra, for our aggregators, but essentially we have our own type hierarchy, where we can have a finer grained control of which types are converts to which types and which types inherit from other types. For example, right, I maybe want to operate on binary as it's a numeric type, and that's why our binary type extends numeric. If I do a binary plus integral operation, I want to maybe get back an integral. Depends on what's conversion function present. And so on. Say I want to do a divide between integral and real. So then we went ahead and said, okay, so we need this base class, base container to contain the types. So we define a container to contain the feature values. And essentially it's just it defines a type, and then it has the def value there to contain the value. And then we have some simple checks there. Is it empty or is it nullable? And then here's an example for text type. Right? So text contains a value of option. It extends a feature type, and then, of course, it defines an option string. I stripped out a lot of functionality from here for things that we actually want to do with them, with features. But this is essentially kind of to give you the idea of what this container is. Then we went ahead and said, okay, so now we need to define a pointer to the data, to the column, as you wish. And this is the feature. Feature needs a type of feature type. And this whole magic actually happens thanks to the type tags. It wasn't possible with previous versions. We couldn't even do it with the Scala 210 because type tags weren't serializable. I don't know why, but they weren't. So now they are, and Scala reflection is actually thread safe, and we can use a lot of things with it. So a feature would have a name, say like a name, a sibling pose, and so on. And then it has an origin stage. The stage actually defines the computation. This is that extract method that we've seen. And then you can transform feature. So this is essentially the map function, that you can provide a stage that will produce you a feature of a different type. And this is how we stitch it. We stitched features together into this computation graph. So let's look on this example again. So say I want to do feature builder.numeric passenger, but then I have to do the name there. So as you've seen in my example, I didn't provide any name. I said we inferred from the val names. So we do it with macros. And the way we do it is this. So it's like a short example of how we do it with macros. So we have this macros helper there, which I stole from SBT codebase. They have a lot of cool stuff there. Go check it out. And then I produce a new tree. I replace the tree for the feature builder with a value name, which proves itself to be a super powerful feature for us. OK, so this is macros. Then we use, so consider we have the types that I defined. Now I want to transform. I want to build sibling poses. I will need to provide some binary numeric transformer that takes two features, and then another one, which essentially gets me the feature size. So can I just write the plus one? Sure. For this, I would define some implicit class, which extends my features of type numeric with a plus operator, where I implicitly create this transformation stage. So users don't see it, no one sees it, but it's there, and everybody's happy about it. It's actually makes quite complex things and types to be hidden into these simple operations. And we actually use another macro here to infer the val name. I'm not showing that because this is actually a bit involved. Code is a bit involved there. So I'm going to explain how it conceptually how it works. So say if you have this expression, sibling poses part, right? Those are two pointers to two columns eventually in the data set. And then when I apply the transformer will produce a new feature. Then I would apply an extra plus transformer with 1 to get me an extra feature. And this is essentially the feature we get. So there is actually this hidden feature there, underscore feature numeric, which nobody sees, but it is present in the data set. So what we do really is that each transformation that we make in our framework keeps adding columns to the different. They are all, we kind of consider data frame to be a mutable piece of data. We never override the same columns. We just keep adding columns. And this realization helped us to not worry about overriding columns at all. So first of all, we did infer the names from features, and then we had this understanding, okay, it's actually cheap to add columns. Let's just keep adding those. And essentially, we'll just only use the columns that user wanted for training, and that's it. The rest columns will be just discarded. So it hides a lot of complexity from the engineers, essentially. What we get from here is actually a graph, right? So again, we get a DAG here where stages depend on features. And from this DAG, we get two stages, which essentially become part of the Spark pipeline. So this is the zest of this whole talk, really. And then the stages, they look pretty much like this. So this is our like a base stage. And this is the stage actually that mix in the Spark world with our world, where we mix in the ML writable and the pipeline stage from Spark ML. But now look, we added types. That's basically the idea. We added the input features and output feature types. And then we take care of transforming the data frame schema underneath. So again, I hide this method because it's pretty involved. But this is what we do for the users. We add columns, we add metadata for the columns, we make sure the types match, and we move on. So we hide it completely from the user's perspective. So for the binary transformer, say we want to compute sibling poses plus sparge again, this is the binary transformer that takes a tuple from features, tuple of features, and produce another feature. So, and then we went there and define a lot of base traits for those. So we need a pipeline stage that produces a single feature. And this is a stage that gets one input and one output. OK. And this one gets two inputs and one output. OK, now imagine this process to do 1 to 2, 1 to 5, 1 to 3, 1 to 2, and so on. So we actually generated a bunch of those stages. It's kind of tedious. But you know, I mean, it has to be done. So we actually went to some sane number, like 5 to 1, 5 to 4, I think something like this. We didn't go like 100 to 100. So if you do it 100 to 100, you probably do it in Ronin already. Because usually you can do 2 to 1, and that's enough. So 2 to 1 and 1 to 1, this is enough. You just don't want to have explosion of stages in your pipeline, which are also, if you use data frames correctly, you happen to leverage the catalyst analyzer. If you guys look at it, it's pretty amazing. They kind of squash maps together, and it all happens really fast, all your computations. So it's not that a big deal. But for certain use cases, we actually needed 5 to 4 stages. So OK, here's an example of a concrete one-to-one transformer. It's actually an implementation of a transformer. This is the guy who mixes actually a Spark transformer here. This is the connector class trait between our stage, which is typed, and the Spark stage. And then look on the interface. I actually find it very beautiful. So for the user, user sees a transform function from I to O. It's completely typed, and then we hide the UDF from him. So this is essentially what we were trying to do here. So, OK, no UDF and no dataset dot with column and then names and then blah, blah, blah. Nothing. It's just hidden. We take care of that, and we just need to make sure your closure is serializable. If it's not serializable, of course, there is nothing we can do about it. We just check for it at runtime before we start the pipeline, which is like as early as we can. When you do Spark submit, we check for your serialization. And so on. So again, we have a lot of combinations here for the different stages, transformers. And then, OK, last code slide. And this is an estimator. So this is another one that provides a little bit different interface that says, OK, user will need to provide a feed function that, given a data set of some I-value type, right? This is the underlying container type. It needs to produce a transform function for me. So OK, go figure out your model to your fit, and then provide me a transform function so I can compute the scores. So this is what it is really. And then, OK, here's an example of what this guy produces. So essentially, Honorary Estimator produces an honorary model, which is a transformer of 1 to 1. All right, this is this new honorary model that we produce. OK. So now let's look how this last stage works in pictures. So when you run pipeline and run the train, we get the data. We extract all the features with the extract phases. Right? We get this data frame first. Then we build your DAG. From all the features that are constructed, we stitch them all together into the DAG. We do topological sort in it, because Spark requires it can't do it on its own, so we have to do it. And then we create a Spark pipeline. Underneath, we just really do a new Spark pipeline, new pipeline, do set stages, sorted stages there. We get the data in, and then everything happens from there automatically, really. You get back your estimator, and then you can use a transform. So going forward, we really want to keep wrapping, or kind of somehow make it easier for us to wrap Spark stages. So right now it's very manual. You kind of open the Spark code base, you look through the code, what's the input, what's the output, you kind of guess the type, then you run a test, maybe look on the test, find out the type. But we do it slowly for the things we need. I would love to see some code gen for the stages we might need to work on. Code gen for macros, I don't know why I put it here. I mean, it is really scary. Macros are a very hairy feature. I hope with Meta we'll have some better APIs. Automatic feature engineering is something that we're working on. to do some kind of better feature selection, like figuring out features in automatic way. And then we actually hoping to abstract off Spark. So we started doing that to move to Apache Beam. How many of you heard of it? But check it out. It's an interesting abstraction layer. So key takeaways for you. So real-life machine learning is hard. Spark is also a great start, but it needs type safety. And once you start building large applications on it, you will discover it really fast that beyond 200 lines of code, Spark code, it doesn't scale well. And you really need to have some type safety for it. Simple and intuitive syntax is the key, and then it saves travel down the road for you. So people can easily argue about their application logic rather than figure out why caching doesn't work or why data frame columns disappear or not present. Scala is quite awesome. So it has all the coolness, especially with macros. Macros and type tags are it's just killer feature for us. And modularity and reusability is the key. In any software engineering project, you want to do good abstraction of your pieces. So if you find that abstraction, that helps a lot. Same as we did with features and transformers and readers, this abstraction helped us to provide a really good library. If you want to learn more about this, so this is the website for our platform, Salesforce Einstein. The Prediction.io website where, well, I didn't mention a lot, but it's like a template engine, so read about it. We're trying to incorporate it with Optimus Prime. And then some more exploratory talks on that, on the Optimus Prime from my colleagues Shubha Nabar and Lee McGuire, which were recorded and published. If you're really curious, so this is our email, and just email us. And yeah, thank you very much for attending. And remember to rate this session. Yeah, that's it. I will take questions after.